So, what do you know? And how do you know it? Something I've been thinking about because of a lecture from a math course I took at university some number of years ago. I mean, there's a point of debate, contemplation, I'm not sure exactly what to call it, to do with belief, knowledge, what's going on. I mean, it seems like believing and knowing are things that we do. So if I believe something enough, does it become knowledge? I don't know. I guess theologians and philosophers and scientists will debate and refine that. But what brought it to mind to me, or for me, like I said, was this lecture for, it was an introductory lecture for a course I took at university called Exploration and Proof. The point of the course is to teach young would-be mathematicians to hone our skills in mathematical thinking and to write proofs. My main focus, interest in math was what's often referred to as pure math, as opposed to applied math. Applied math tends to be stuff where people are actually trying to accomplish something, like to assist in building bridges, launching rockets, do financial stuff, whatever. Pure math tends to be goofballs like me who are really more interested in math for math's sake. We're not the only ones that are into the beauty of math, but that kind of seems to be enough for us. We don't really care to do anything practical with it. Anyway, so this course, if you're doing pure math, you do a lot of thinking about math, and then you've got to write proofs. So the point of this course was to get good at thinking about math and then writing proofs about whatever it was you were thinking about. And in the introductory lecture, the first day, the professor opened up the lecture for discussion. The small course. It was a small class. I think there was like, half dozen of us, maybe 8 people. And you get to that level of math, there's just not a lot of people that are that terribly interested. We tend to be a rarefied breed. Anyway, so she asked us, what is math? What do we think it is? And of course there were a lot of things, bandied about, the things you might expect. I mean, this quantitative reasoning, systems of logic, yeah, sure, I could probably come up with a few more things that were bandied about, but you get the idea. I'm sure you could all probably sit and think about what really is math. Anyway, so after the bit of discussion and going around the class, and she gave us a definition that she liked or was offering up for us to consider, and it was that mathematics is the art of knowing the knowable. I really dig that. There's a certain level of arrogance to it that just seems really funny and cool to me. I mean, that's a common thing in universities that at least I found that people often have a perspective that is furthering the supremacy of their discipline, if that makes sense. I mean, physicists tend to think physics is, the thing that everybody should study. It is, the best way to understand the universe, and chemists and biology, everybody's got reasons for why they think their discipline is the best. Which is fine, This particular professor was, she was very into encouraging an interdisciplinary perspective. Yeah, anyway. So, she wasn't really trying to talk about the supremacy of mathematics and, it's the art of knowing the knowable, making it seem like, it's the ultimate course of study. But when you're talking about pure math, one big feature is that mathematics is an axiomatic system. Yeah, okay, so what is an axiomatic system? It's a system based on axioms. Axioms are simply just a set of rules that they're sort of the starting place. You gotta have some rules, and you start with those rules, and then from axioms you develop theorems, and then you get a whole bunch of stuff going on. So why axioms? Well, math also is, at least attempts, I think it succeeds, but, who knows, if us humans are maybe not as smart as we like to think we are, but it needs to be logically consistent. Not just because math geeks like me want it to be logically consistent for a sense of beauty and a philosophical notion, but it needs to be logically consistent so that it does need to be useful, right? I mean, if math wasn't logically consistent and predictable as far as, well, if you got varying results, how would you ever do any accounting or build bridges? Or, I think you get the idea. Common sense tells you it needs to be logically consistent. But there's a thing in logic that you can't say something is true just because it's true. That doesn't fly. It's true because I said so. That's not a good thing. But there's a need. You gotta have something to start with. So how do you get around this thing? I guess to illustrate the point, have you ever done the dictionary circle with definitions of words? I can't think of a good example right now at the top of my head, but if you look up a word and in the definition you find another word that you don't understand, and so you look up that word, and and you can kind of go around and around, and because a dictionary uses the very words it defines inside of the dictionary itself, you kind of have to put together an understanding of the definitions using context. And language is a little more forgiving in that sense. Language doesn't have to be logically consistent. Language, part of the beauty of language is that words can have multiple meanings. In poetry, often people misuse words on purpose to convey meaning or emotional content. But for math, it needs to be consistent. Again, back to that idea of logical consistency. So to get around this circular definition thing, there's an accepted idea that you start with axioms, and the point of the axioms is that you start off with the smallest possible set of things that you need in order to build your system, and that those rules need to be simple enough that they're kind of self-evident. I don't know how many of you took geometry through your educational careers, but if you remember, there was, rules in geometry, and you probably even had to write some proofs, I'm not going to spend too much time on this. I didn't intend for this to be a course in mathematics or something like that. It's just, me babbling about some stuff that I was thinking about. But you could Google Euclid's Elements, and it'll give you some rules and then theorems and whatnot. And the things it starts with is, like there are points, and then there are lines that connect those points. And a really famous thing in geometry is that the rule about parallel. The common one for Euclidean geometry is that parallel lines never cross. They, if two lines are parallel, they're, parallel, right? They don't ever cross each other. And you might think, well, that's obvious. And it's like, yeah, but it needs to be said in the axioms because there are other geometries. Spherical geometry, hyperbolic geometry, where the parallel rule isn't the one you're used to. And those forms of geometry are logically consistent and useful. They're just less common than the Euclidean plane geometry that, were typically taught in, I think high school is when I first got exposed to that. Maybe junior high, I think high school. Anyway, if you ever took that course or can remember back to that, you kind of get an idea of the idea. So you have these axioms, basic rules that you start with, and it's sort of like, think of it like a game, a big, complicated, in my opinion, beautiful game. So you have rules to start with. And everything comes from those rules. You develop theorems. Well, that's what it is. You develop theorems, and then there's ideas and things that come from those theorems, and you start doing things like you could have, curves and graphs and all kinds of really cool stuff. So what does this have to do with that art of knowing the knowable? Well, that's it. That's really the crux of it, is everything in math, which, in typical math, like most of us are used to dealing with, is using the real numbers, like the number line. You've probably all seen that, with 0 and 1, 2, 3, and then negative 1, 2, 3, and there's all the numbers in between, the fractions, and of course the irrational numbers like pi and whatnot. And you can do calculus, and you can do, build bridges, launch rockets, do banking, whatever. So all this really cool, groovy, beautiful things come from a very small set of axioms, and we mathematicians say we know these things to be true because they are logically derived from, starting with the axioms, using rules of logic to develop this knowledge. So there's the thing. At that point, there is an understanding of what it means for it to be knowledge. It's not just that you believe it, but that it's demonstrably true. So it's knowable. And kind of the art bit, I think, as well as to do with, because math is less of a science and more of an art, really. You don't really do experimentation in the same way that you do, say, in physics or chemistry. I mean, you can experiment, trial and error, that kind of thing, but you don't have to reproduce things. You know, in science you come up with the theory, and then, well, maybe you make some observations, and you go, how does it work? And then you have a theory, you come up with a way of testing that theory, some experiments. And the idea is that something about your experiment will reveal something about your assumption, your hypothesis, and you can go, yeah, cool, see, this confirms my hypothesis. But in science, it needs to be reproducible. So you can go, look, I think this is true, here's my experiment that shows it, and I have a result. And then some other guy can go, I think you might be full of it. He can now reproduce your experiment, and if he gets the same results, and if you reason things through and made a good argument, he'll go, yep, I guess that is true. And, onward it goes. Yeah, you don't got to do that. You can sort of think about things and whatever, and you come up with an idea and you write a proof about it. But if the proof is well constructed and logically consistent, that's it. Nobody has to reproduce it. You don't have to do it again. You could just read it and go, yep, he's right. And voila, and then the next guy can go, hey, but that eye gives me another thing. And then you develop on, it goes on and gets big and complicated and beautiful. And anyway, so I guess there's the art bit about it. But it is, knowing the knowable is based upon those axioms. So it's kind of a big if then. See, if you don't buy those axioms to begin with, set up these rules, like in the geometry thing, and somebody says there exist things called points, and if you have 2 points, there's a line between them that is unique. And if you go, yeah, I don't buy that, I'm gonna get, because there's a thing, it seems, there's such a thing as points, and then lines connect the points, and this is all fairly basic, rudimentary, at least that's the idea. The intent is that you kind of go, oh, sure, I'll buy that. But if, you get some character that goes, no, I'm not going to buy that, there's no point in really even arguing with that guy. I mean, you need to buy the axioms in order for the rest of it to follow. It's gonna, if you accept these things as true, then the rest of everything else follows. And if you're not going to buy that stuff, then, well, like I said, what do you mean you don't believe there's points or lines? What? Are you nuts? I mean, I suppose there's somebody, I've never come across anybody who wouldn't accept basic axioms. I mean, short of people just trying, devil's advocate kind of deal, and just to be a curmudgeon and say, nah, I'm not going to believe you. Sort of, but I've never met anybody who, from a serious academic standpoint, went, I don't buy those axioms. Well, with the exception of, I referred earlier to the rule about parallel lines. But that's a subtle thing, and I'm not going to get into that. I think it requires a certain level of discipline and sophistication that I'm not really ready to exert at this point today. So what was the point of all this? I'm not entirely sure. I was just thinking about, well, like I said, that lecture from, wow, let's see, more than 20 years ago anyway. Who knows how long? I am an old curmudgeon now. Yeah, well, see, now I think I had a point that I was going to try and get to with all of this, and somehow it is, well, evaporated like so much nicotine vapor. Well, you know, since I seem to have addled my brain to the point of not remembering my point, I guess I'll go ahead and call this quits for today. At least I'll have some thing to post up, and yeah, so there you go. Hopefully you found this worth watching.